In this lesson, we'll be continuing our work with right triangles, looking at special right triangles. One of the special right triangles is the 45-45-90 special right triangle. And in this example, we can derive the relationship. Derive means make sense of it, come up with the relationship on our own. Determine the angle measures and the exact missing side lengths of the right triangle that's shown here. So a couple of things to pay attention to. One, it's definitely a right triangle because of the right angle symbol. Secondly, it's an isosceles right triangle because of these tick marks. So because the height and the base are congruent, the base is also going to be 7 meters. Something else that we should pay attention to. Because it's an isosceles right triangle, we know that in isosceles triangles, base angles are congruent. We also know that the sum of the three angles in any triangle is 180 degrees. 180 minus 90 is 90. These two congruent angles have to measure 90 degrees. So we can take 90 degrees and divide that by 2, and we know that each angle measures 45 degrees. Now we've found the angle measure, we need to find the missing hypotenuse. And one thing in a right triangle, if you're never quite sure how to proceed, you will be able to typically use the Pythagorean theorem in some way. So when you're stuck, try a squared plus b squared equals c squared, where a and b are these leg lengths and c is the hypotenuse. So let's substitute in 7 and 7 for the two legs and leave the hypotenuse as c. Now let's square the number 7 before we add, because of order of operations, exponents before addition. 49 plus 49 is equal to c squared. Now we can add 49 and 49 together, and that will be 98 is equal to c squared. Now we want to take the square root of 98. And the problem is, if I use my calculator to do that, I don't get an exact value. It's around 9.899, etc. But this is an irrational number. The square root of 98 is an irrational number. So we want to write it as an exact amount. And to do that, you want to think about rewriting 98 as the square root of some perfect number, perfect square number, times another number. And so 49 times 2 is going to be 98. So we can rewrite the square root of 98 as the square root of 2 times the square root of 49. Now the square root of 49 is something that is an integer value. It's a whole number. And so I can simplify the square root of 98 as 7 times the square root of 2. That is the exact value for c, 7 root 2. And what we want to do now that we have the exact value of the hypotenuse is we want to think about what is the relationship between the sides of a 45-45-90. Well, we have two sides that are always going to be congruent, and the hypotenuse is going to be the square root of 2 times the leg length. So keep that in mind when we solve for 45-45-90 special right triangles. There's one other type of special right triangle. It is a 30-60-90 special right triangle. In the 30-60-90, one of these angles is going to be the 90-degree angle, and the other angle is 30, and the smaller 30 is the smaller angle, and the larger of the two angles is 60. So we can look here at our equilateral triangle. And what we can do on this equilateral triangle, where every side measures 8 units, is just drop a perpendicular from the top vertex down to the base. When we do that, we are looking at a right triangle. We don't know the height, we will know that half of 8 is 4. This is going to be 4. And we know the hypotenuse is 8. So to find the height, we can use, once again, the Pythagorean theorem, where a squared plus b squared is equal to c squared. And we can substitute in a is 4, b is h, and c is 8. We can square the numbers 4 and 8, 4 squared being 16, 8 squared being 64. And if we want to solve for h, which is the height of this particular triangle, we can subtract 16 from both sides. 64 minus 16 is 48. But once again, when I take the square root of 48, this is not a perfect square. The closest perfect square to 48 is 49, and the square root of 49 is 7. So the square root of 48 would be a little bit less than 7, right? But that's not an exact value. So the square root of 48 is a little less than 7. The exact value for the square root of 48 can be found out by rewriting 48 as the product of a perfect square times another number. Now we know 16 times 3 is 48. And if you didn't know that, you could start dividing 48 by some perfect squares, and you want to divide it by the biggest perfect square that is a factor of 48. And the square root of 16 is 4. And so this height is equal to 4 root 3. What we want to do now is remember that this was a 30, 60, 90 right triangle. This angle measure right here is going to be 60 degrees. How did I know that? Because this was an equilateral triangle, and in an equilateral triangle, each angle measures 60 degrees, but the top angle, which was 60, we have now divided into 2 equal parts. So over here, this angle is going to be 30 degrees. So what is the relationship in a 30, 60, 90 right triangle? Now let's take a look at these numbers and let's see how they relate to each other. So it looks like there's going to be a short side length, right? It's the shorter leg. And it looks like this short side is always opposite the smaller angle, right? So the short side will be opposite the 30-degree angle. If I know that short side, the hypotenuse is double that, so 4 times 2 is 8. And the longer leg is whatever the shorter leg is times the square root of 3. So we're going to keep that in mind, and we've just derived that relationship. Now let's take a look at an example where we apply this. First, the 45, 45, 90 special right triangle. Most reference sheets will give you something like this, a diagram, to help you remember that in a 45, 45, 90 right triangle, the hypotenuse is going to be the leg length times the square root of 2. And so x here is going to be 3 times the square root of 2. Now, what if I know the hypotenuse is 10 root 2? Then the legs are going to be this hypotenuse divided by the square root of 2. Therefore, each leg is going to measure 10 units in this particular example. So that's how we handle applying the relationship of a 45, 45, 90. Now let's look at the 30, 60, 90. The relationship that we derived earlier is shown here in the diagram. Remember that the 3 angles of a triangle will always add together to equal 180 degrees. So this little angle that's not shown is actually 30 degrees. If I know the hypotenuse, which is the longest side in any triangle, the side opposite the 30 degrees is going to be half of that. So this side is going to be 8. And then the longer leg is going to be 8 root 3. Remember, it's the root 3 relationship in the 30, 60, 90. In this example, we know what the side opposite the 60-degree angle is. And when you look at the 60-degree angle in the reference sheet, and we know the side opposite the 60, then the side opposite the 30 is just going to be whatever is in front of the square root of 3. So 9 is going to be opposite the 30-degree angle. And we need a lot of practice with these, right? And then the hypotenuse is always double the short leg length. So 9 times 2 is 18. My hypotenuse here is going to be 18 units.